Okay, so there are many different models of evolution. Some apply to nucleotide data, some others apply to amino acids. So here we're going to see the simplest evolutionary model designed for nucleotide data, and it is called JC69. JC69 stands for Jukes and Cantor. 1969 is the date when these two authors published a paper describing this model of evolution. So it's the simplest model, and it has a single constant rate for all substitutions. So all mutations from one nucleotide to another have same rate, occur according to the same rate. And this rate is commonly known as alpha. Alpha is a positive number, and that wouldn't be really useful to have an alpha equal to 0. It means no evolution. An amino acid, a nucleotide, A would remain indefinitely an A, and there would be no mutation. So alpha is strictly bigger than 0. This model models only substitutions, no insertions and deletions. And generally speaking, it is the case of all models of evolution commonly used for to build phylogenetic trees. The case of insertions and deletions are treated as the case of one character, nucleotide, being aligned to a gap, and there's a specific way to treat this. But the probability of an insertion itself is not modeled as such. So the model explains or creates only ungapped alignments, and since this model has only one parameter, it can be trained on relatively small data sets. I haven't mentioned this, but the complexity of a model is directly proportional in a way to its number of parameters. And the more complex your model, the more data you need to train it so that it's an accurate model. Here, because there is only one parameter, it's the model of choice, especially when you have a very scarce amount of data. This is obviously an oversimplification of the reality. Observations give credit to varying substitution rates depending on the position in the genome or in the tree of life. So it wouldn't be really sound to build one phylogeny, a huge phylogeny, just with JC69 on many taxa belonging to different kingdoms, for instance. Okay, but nevertheless, this model gives results that are not too far from the results given by better models in many cases. And it has very simple math to calculate the probability of one sequence having evolved into another one, and that's why I decided to show for this introductory course this simplest model of evolution. So evolutionary models are commonly described by means of a matrix. This is a matrix of instantaneous rates. So these rates, alpha here, are positive. So in this case of the JC69 model, there is only one rate. Okay, that's alpha. Here you see, so it's a matrix of 4 by 4, 4 by 4 because you have 4 nucleotides, and the alphabet is ACGT, and the rows denote substitutions from a single nucleotide, and the columns are substitutions to a certain nucleotide. Okay, so it reads this way. Here, for instance, you're in the row G and in the column C, so it means it's the instantaneous rate pertaining to a mutation from G to C. Okay, this one is the instantaneous rate from A to T. Okay, QAT. It's very common to call this matrix the Q matrix. The rows must sum to 0, okay? The sum in each row is equal to 0. That's why this number that is not interpretable as such really conveniently, because we cannot talk about a mutation, an instantaneous mutation from A to A, for instance. It doesn't make any sense. It's not a mutation. But for some mathematical reasons, any matrix of instantaneous rates must have all its rows summing to 0. So you can think about this as a placeholder, but if you want to give a value here, it's minus the sum of the other 3 elements on that row, okay? So you have minus 3 alphas there. What does it mean to talk about instantaneous rates? The model assumes that over a very short duration, dt, a very short amount of time, the probability is that a nucleotide, for instance, A mutates into a C, is this instantaneous rate times the amount of time, okay, of small amount of time. So you have a probability alpha times dt that a nucleotide A mutates into a C. Because you have only one rate here, there is equality between this and that. You also have a probability alpha times dt that the nucleotide A mutates into a C, okay? So you have probability 3 times alpha that there is a mutation during an infinitely small amount of time dt. Okay, that's the instantaneous rate matrix. From this matrix, we can calculate, this is a complete description of the evolutionary model. And you'll see that we can perform some calculations using the rates in this Q matrix. It's easy to calculate from these instantaneous rates and the definition here. It's easy to calculate how would a population of nucleotides evolve given this evolutionary model. From a time t equals 0, let's consider a population of uppercase N nucleotides, and there are some A nucleotides, some C nucleotides, some G nucleotides, some T nucleotides composing this population. And it evolves from time t is equal to 0. Okay, let's imagine you have a soup of nucleotides, a mix of nucleotides that are subject to this evolutionary model, and let's see how this population changes, okay, over time. So over time we have lowercase n and subscript d nucleotide, a certain nucleotide, at a time t. That's the count of that nucleotide at time t. Okay, the number of the nucleotides that is of type A, adenine. So at any moment in time, okay, there is no nucleotide that disappears, there is no nucleotide that is created. They just evolve and potentially mutate. So at any moment in time, NA of t plus NC of t plus NG of t plus NT of t is equal to uppercase N. Okay, this is our total count of nucleotide. With some calculus, we have this that comes as a relation. This is the number of adenines at time t, and this was the number of adenines at time 0. Okay, the initial condition, the initial setup. Out of this uppercase N nucleotide at time 0, we had this amount, that's an integer, a number, of adenines in our mix. Here we have this uppercase N divided by 4, not necessary to explain this. Here we have an exponential of minus 4 alpha times t, okay? And t is this time that elapsed between time 0 and current time t, okay? So this expression here pertains to nucleotide, A, adenine. You have also exactly the same expression for adenines, for nucleotides C, G, and T, okay? Cytosine, guanine, and thymine. So what can we say from this expression? From this expression, we see that, okay, the proportion of a certain nucleotide at time t depends, of course, of the initial proportion that you have of this nucleotide and of the time that has elapsed, okay? Plus the alpha parameter, that is our single parameter for the Jukes and Cantor 69 model. But what we see is that if we let this mix of nucleotides evolve indefinitely, then we have plus infinity here for t, exponential of minus infinity is 0. So at time n, when time t, tends to infinity, to plus infinity, we have this quantity that tends to be equal to this n over 4, okay? This means that this Jukes and Cantor 69 is a stationary model because there is a horizon distribution of nucleotides, and this distribution of nucleotides is the uniform distribution, 1/4, 1/4, 1/4, 1/4, okay, for each nucleotide. So that's why after an infinite amount of time, the quantity, the number of nucleotides A tends to be equal to the total number of nucleotides divided by 4. And same for C, same for G, same for T. So we have established that JC69 is a stationary model. So that's what we call pi subscript A for this model, okay? Pi is the letter that we use to describe the values of the stationary equilibrium frequencies, of nucleotides. There is a key tool, mathematical tool, that enables us to move from instantaneous rates to probabilities of change, okay? These are instantaneous rates. The probability to have a mutation from A to C over time dt is alpha times dt, okay? But this dt must be an atomic amount of time, a very small amount of time, okay? It doesn't work to say the probability of a mutation from A into C over a long time t is alpha times t. That's wrong, okay? And what is supposed when we talk about instantaneous rates is that we cannot have two mutations during one single atomic duration dt, okay? We cannot have two mutations taking place. So it's very different when you observe a long amount of time. During a long amount of time, you may have several mutations at the same site for the same nucleotide, okay? So we have to find out how to calculate the probabilities that, starting with an A, for instance, at a certain time 0, after a time t, I have a C, okay? That's a very different thing. We're not talking about individual mutations. We're talking about the fate after an arbitrary amount of time t, the fate of a nucleotide that was initially A, okay? It may have undergone several mutations. So the beauty of the Q matrix is that it gives you straightforwardly, with one matrix exponentiation, these probabilities, okay? So we have the matrix exponentiation of Qt that is used here, and you take out of this matrix. Okay, matrix exponentiation is an operation that takes a matrix as a parameter and produces a matrix also. Okay, so Q is a matrix, you multiply by T, meaning you multiply all coefficients by T, and then you find its exponentiation. It's usually performed by first diagonalizing the matrix. Okay, so once you have this EQT, then you take its value on line A, column C, okay, the first line and the second column, and you have this probability to have a C after a long time T from an initial nucleotide being an A. So lots of this is a key operation in all softwares of phylogenetic reconstruction, because we spend our time, or these softwares spend their time calculating those kind of probabilities to calculate what's the probability of a tree, or the likelihood of a model. Okay, so it's this operation here is key to many software like PhyML or XML, all the software that perform phylogenetic reconstruction. So as I said earlier, the probabilities for the JC69 model are these ones. Okay, 1/4 for each of the 4 nucleotides. So back to our initial problem. We had 2 sequences, and we wanted to infer from these 2 sequences that were aligned. Remember, it's a slide way back, slide number 12. If you have this sequence aligns with this one, what is the evolutionary time separating these 2? Okay, what is your best guess at the evolutionary time separating these 2 sequences? And we had a first naive distance that we calculated just by observing the ratio of sites having a mutation divided by the total number of sites. But we know that it's only an estimation. That is an underestimation of the evolutionary time, because there may have been several mutations on sites where you have 2 different nucleotides aligned on each other, and even on the sites where seemingly it's the same amino acid, nucleotide, you may have a mutation that happened, a double mutation or a silent mutation. So now, thanks to our model, we can calculate things a bit more accurately, and we find this. I don't ask you to establish this formula, but we find that if P is the proportion of observed differences between 2 nucleotide sequences, the edit distance, our good old edit distance that was in our case equal to 0.3, we find that in reality, the expected number of mutations per site, according to the Jukes and Cantor model, is this D. And D is equal to minus 3/4 of the logarithm of 1 minus 4/3 of P. Okay? And this can be shown that to be strictly bigger than P. So what it says is that the expected number of mutations per site, expectably, is greater than what we actually see in terms of observed differences between 2 sequences of aligned nucleotides. Okay, so keep in mind that when you just consider the observed differences between 2 nucleotide sequences, you underestimate the real amount of evolutionary divergence in terms of expected number of mutations per site. So in order to get proper geological durations, remember that we had this problem that we are working on establishing phylogenies with branch length that denote expected number of mutations per site. In order for us to get to proper geological durations, we have to calibrate the rate of mutations. We have to understand, okay, if I have a branch saying there is an average of 0.3 mutations per site, to how many million years does it correspond? Okay, so in order to do that, we need to establish phylogenies with known fossils and fossils that we can date on using other type of evidence, like geological evidence, in order to calibrate to say, okay, these amount, whenever I have 0.3 mutations per site, this corresponds to a geological time of I don't know how many million years. Okay. And then if you expect that this mutation rate is constant throughout your phylogeny, then you can tag all the internal nodes of your phylogeny with actual dates. Just to give you an order of magnitude, on some data, I don't remember exactly what kind of alignment I got this from, but in most DNA alignments, if it's not very quickly varying, very quickly evolving organisms like viruses, I think it's from mitochondrial DNA of mammals or something like that. I got this 10 to the power minus 9 mutations per site and per year. Okay, so if you have this rate, then you can transform your measurements that are in terms of expected mutations per site. You can transform these into geological times. Let's have a break before the final slides.